We are in the, because I'm looking at the wrong thing, the gnarly problems track. And today we are hearing a talk on torturing OpenSSL by, I will try to do this right, Valeria Bertaco. So without further ado, here she is.
Good afternoon, everybody. I'm Valeria Bertacco. I'm a professor at the University of Michigan. And the project I'm presenting today was developed together with one of my students, Andrea Pellegrini, and one of my colleagues, Todd Austin. And we actually were trying to do a reliability project, which ended up being a security project. I'm going to discuss what we did. So as everybody who attends this conference is very well aware, cryptography is all around us. Every time you go online shopping, every time you send an email, when you do your internet banking, even in password nowadays, there is some security mechanism. And also on a lot of consumer devices, particularly game consoles and, for instance, Blu-ray disc players and, in general, media players. There is a lot of money in cryptography, and you just need to go through the expo floor to realize all this. These are some of the data from a couple of years ago, things I could Google from the web, on the amount of money and employment that is related to making sure things are secure. So the project we are going to discuss today focuses on RSA authentication. I'm going to give you a very short overview, just so we make sure we use the same language. So let's say that Anna over there wants to communicate with her friends and make sure that the communication is secure. So she wants to send a message, let's say, to Bobby. How do we make sure that the communication is actually authenticated? Which means, how does Bobby make sure he's actually talking to the person he thought he was talking to? In asymmetric cryptography, which is an approach to this problem, Anna will generate a set of 2 keys. Now, they look like keys. They're really just a very long string of bits, often 1,000 bits or so. But it could be longer, it could be shorter. One of these keys is called the public key. The other is called the private key. What Anna does is she sends the public key to everybody, and she keeps the private key for herself. Then whenever she wants to talk to one of her friends, she will encrypt a message with the private key, send it over, and the friend can decrypt it with the public key. Now, the friend will know it is actually communicating with Anna because only his public key can get the original message that Anna sent. How does it work in practice from a more mathematical point of view? So the 2 keys are two numbers. And how do we generate the keys? Well, first you need to generate 2 large prime numbers, let's say P and Q. You compute the product of these numbers. Now, that's kind of the key of the whole thing. If it's easy to extract the 2 prime numbers from n, then the whole thing falls apart. You need to find 2 prime numbers that are very long and very complicated, so it's hard to factor the number n. And then, from that, you can choose 2 numbers, d and e, that satisfy the property that I show over here. This property is nice because if I take a message and I elevate it first to the power of d and then to the power of e, I get my message back. And so if d is a private key and e is a public key, Anna first elevates it to the private key, and then her friends just elevate it to the public key and gets a message back. And know, oh, I sent a message to Anna, I came back the same. That must really be Anna. It's not somebody spoofing that person. If I'm talking to my bank, oh, that's really my bank. It's not somebody else posing for my bank. That's the beauty of this whole thing. So it's very important that the bank or Anna keeps the private key super secret and doesn't give it to anybody. The private key is the number D and the number N. And the public key is given to anybody I want to talk to. So that all these people, when they want to talk to me, they can actually make sure they're talking to me and not to somebody else. And the public key is the number E and N. OK, so this is my very short overview. Now, in a normal situation, the authentication works like this. Bobby generates a message, send it to Anna. Anna will encrypt it and send it back. Bobby will decrypt it and say, oh, that's my original message, so I'm really talking to Anna. And then we can keep talking. So I would, for instance, trust to send my login and password to the same place. But things don't always go that nicely. People have been trying to attack these algorithms in many different ways. So for instance, some people have been trying to attack the algorithm itself. In 2009, some researchers were able to actually break RSA authentication when it's 768-bit long. And the way they did it is by factoring that product, that number n in the two numbers p and q. So they just brute forced it. It took many compute years. And based on their estimate, it would take another decade or two before somebody could actually brute force a 1024-bit RSA, because it became exponentially more complicated. Other people have been trying to attack the implementation of RSA. For instance, through side channels attacks, where I start monitoring how long does it take to encrypt or decrypt. And maybe from there I can guess some things about the key. Or maybe I can monitor the activity on the circuit while it's doing the encryption or the decryption. There are chips out there that actually can track when somebody is trying to perpetrate a side channel attack, and they protect against them. Those tend to be expensive chips. So consumer electronics and embedded devices usually don't have this, because then the cost of the device would be prohibitive. Other type of attacks are fault-based, meaning instead of trying to observe what's going on while the server is encrypting a message, we try to make the server do mistakes and see if we can get some information about the private key D based on the mistakes it makes. And that's exactly the direction we went. So mistakes. It's easier said than done, because I need the right type of mistake at the right time, look in the right way, and that's not really super easy. So let me show you a little bit what has been done before us. And before I even do that, I want to tell you these mistakes and how they work and what type of things are these faults. So in general, there are transient faults and permanent faults. Permanent faults is when a transistor breaks in a chip forever. You don't want any of those, because then the server is broken, it's not going to encrypt anything anymore. Your key is gone with the server. You want transient faults, which are temporary failures in a wire or a register or a transistor, usually very short in time, typically shorter than a clock cycle. And actually, a lot of transient faults don't have any impact at all, because they dissipate before the new values, the results of the computation, are latched in any register in the chip. But if there is a failure that occurs at the right time, and that does not dissipate before the next clock cycle, then an erroneous result will be stored in the chip. For instance, an erroneous encryption. How do faults occur? Do we really need to worry about this? Well, most transient faults are due to particles in the air, alpha particle, cosmic ray, energy particle that are present everywhere. But they are not very dense on the surface of the Earth for the most part. If you live in Denver, you're at higher risk, because it's a higher altitude, and so there is a higher density of alpha particle and energy particle in general that can create transient fault. If you're on an airplane, it's a little bit higher too. But if you are in outer space, then they're really dense. Then you get beaten by transient fault all the time. So you would say, OK, transient faults are not really concerned. I have bigger things to worry about. Probably my RSA authentication is going to work well. But then we said, maybe we can create some of those transient faults. Maybe we can make the bad stuff happen so that we can extract the key. Is that possible? We don't want to sit there and wait for a cosmic ray to hit. That may take many hours, many days, many months. But maybe we can provoke these things. So what can we do? Let's say, and I'll get to it, but let's say magically I can make faults happen. People have been trying to explore this line of research. So a few years ago, Bonnet and others proved theoretically, meaning mathematically, that if you can create faulty situation of the right type at the right time during the encryption with the right qualities, then it would be possible to extract some information about an RSA private key. And they particularly showed this for the Chinese-remanded theorem algorithm, which is a classic algorithm used to implement RSA authentication because it's very efficient, computationally efficient, so it's fast. You don't want to wait forever for your message to be encrypted. So it has a good benefit there. So they showed this mathematically. They didn't actually show it on a real system. Other authors, in about 5 to 3 years ago, depending on the range, demonstrated actually this attack physically on real systems, particularly attacking microcontrollers and smart cards. So specific devices that tend to be simpler than a microprocessor, that do not run an operating system, but they are still valuable in being able to create correct RSA authentication because people use them to authenticate, such as smart cards. Okay, so that was actually definitely a really relevant type of attack. Now, how do these attacks work? Particularly, how does the main idea of that theoretical attack work? Well, the idea is this. I have a server, and I have a client. The server has a private key and the public key, but it is not relevant now. And the client has a public key. So the client sends a message to the server. The server authenticates that message by signing it with a private key, obtaining the signed message S, and send that message back to the client, which uses the public key to decrypt it and obtain the original message M back. It matches with what is sent originally, said they are the same, I'm happy, I'm talking to the person I really meant to talk. When something goes wrong, this is what could happen. So the server does an erroneous authentication. So the client sends a message, the server attempts to encrypt, but during that process, a fault is injected. So the result is an incorrectly signed message. That message goes back, the client decrypts it, and does not obtain the original message M, obtains something different. So identify that that's an incorrectly signed message. And from that incorrect signature S hat, it is possible, in some situation, to extract a few bits of the private key. So that's just the beginning, but if I can have the right situation many times and I get a lot of the messages of this type, then a little by little I can extract the entire private key. And that's the hope here. So this is my setup. I'm going to explain how it works. I have it all here on the table. That's a picture. So this is my client. This is an RSA client. It's, I don't know if you can read that. It's an Intel quad-core machine running Linux Debian and the OpenSSL library. And it sends messages to this guy here, which is my RSA server. Now, this is also a microprocessor. It's a microprocessor mapped on a FPGA. An FPGA is a field programmable gate array, basically a chip that can be programmed to be anything we want. And what we did is we programmed it to operate as a Leon 3 system on chip. That's a publicly available system on chip design, which includes a Spark microprocessor, an Ethernet port, a serial port, and it's basically a complete computer. Now, the downside of using an FPGA instead of the real chip is you cannot go that fast. So this thing is only operating at 40 megahertz. You probably don't want to buy it. Well, you don't want to buy it if you're trying to run Linux and do real stuff with it. We actually were able to play Doom. Yeah, you need some patience, but you have more time to shoot. Okay, so this is a complete microprocessor. It runs Linux and is connected through this Ethernet switch, through a normal Ethernet network to my client. Also, I boot the operating system using the network and using the USB drive that I have back here, which is only connected to my client. Okay, and then this is my other piece of equipment. This is a voltage controller. See, maybe I can lift it a bit. Many companies do this. Well, a handful of companies make these things. It's by Agilent, and it costs about $1,000. I just looked at this specific model on the web. I'm sure you can get some cheaper with fewer features. In our case, I work in a computer architecture lab, and so we have things like this laying around, and I grabbed it. Okay. You probably can see it on the face of that. I have this button here is a voltage controller, so I can regulate the voltage that I feed to my microprocessor. And the display tells me what the voltage. So right now, I'm setting a nominal voltage of 1.5 volts. So I'm feeding this power to my microprocessor, 1.5 volts, which is a nominal voltage you should have. So it should work just fine. What I have here are two interfaces. This is just a standard interface for the serial port of my server microprocessor. So you can see that indeed I have a prompt there. My server is called Sparky. And my login is my student login, Andrea Pellegrini. And this is just a Java program running on the client that helps manage all this communication. So you don't just see signatures running everywhere, but we get a summary of what's going on. So just to start, I'm going to ask the client to send 100 messages to the server, asking the server to encrypt them. When they come back, the client will decrypt them and check if they are authenticated correctly or not. So as you see, the messages go through. Now we see on the interface all the messages coming back encrypted. Also, you can see that I want to send a total of 100. So far, I received 67. And they were all corrupted. So let me see if I can reset this. I would really like not to have them corrupted. OK. This is good. They're all coming back clean. They're all perfectly authenticated. And there is nothing I can extract from these messages, because when I decrypt them, they are the original messages I sent. Now, I'm going to proceed with my presentation a little bit, and then I want to show you another aspect of this. So the RSA server is a Spark V8 running at 40 megahertz. I have the voltage controller, the network switch. This is how I brought all this equipment to the conference. I was so scared that it would break and I wouldn't have anything to show you. So I took the diapers of my baby and patted everything, every way I could. Yeah, and then left the baby home. OK. So a little background here on logic design and electronic design. So in every digital system, there are flip-flops everywhere, registers that store values. Every time the clock signal ticks, values come out of the register. They do a bunch of computation through combinational logic and or XOR gates. And they should reach the next set of register before the clock ticks again. So if that happens, we are storing the correct results. And this is actually what usually happens in everything you normally buy if you operate it at the correct voltage. But if you lower the voltage, you're giving less energy for the signals to propagate. As a result, some signals, particularly the ones that have a longer path to traverse, may fall a little bit behind and may not reach the registers in time. So in my little setup here, I was operating at 1.5 volts. If I lower my voltage, I'm now operating at 1.28. I'm going to tell him, do 100 messages again. Now, some messages are corrupt, not all of them. But enough that maybe I can extract something from my system. The lower the voltage, the more messages will be corrupt. So for instance, right now I am at 1.28. If I go down to 1.24, I expect to see many more corrupted messages. Oh. Sorry, let me reset. Sometimes when you get too warm, it's getting a little bit glitchy, so I'm restarting it for cleanness. OK. Oh, let me move the interface so you can keep seeing that. I'm going to continue presenting while this is completely restarting. Hopefully, we'll cool down a bit. So OpenSSL authentication, like how do this fault exactly work and how do I get the right type of fault to do what I want? Well, in OpenSSL authentication, the standard process is this. OpenSSL uses the Chinese-Remanded theorem program, algorithm to do the authentication. Then it checks the results. If that algorithm did any mistake, then it uses a fixed window exponentiation to redo the computation. It's a more complex approach that takes more time, but is much more secure. It's very easy to attack the CRT algorithm. So we went to explore directly the fixed window exponentiation algorithm. And this is how it works. The private key is partitions into windows. And the algorithm here goes, and basically the goal is to compute m to the d. So it takes the message m and continues sorry, let me go back for a second. It computes first, well, let me show you this line first. First it does the message, the sign message at the beginning is 1. We multiply that by m to the first window, the most significant window. Then we have to shift those bits by doing a squaring, an iterative squaring on the temporary message we have. So what we basically do is, first we take the message and we create an exponent 1101. Then we shift that by 4 position, and we create the next, multiply by the next exponent 1011. Then we shift by 4 position, etc., etc. So I have a little example here with a short key of only 8 bits. The beginning my sign message is 1. I come here, for the first iteration, there is no squaring to be done. And then I multiply by that m to the d for the first window, 1101. By the way, as soon as the message arrives, we can pre-compute m to the power of all the possible values in any possible windows. So we have a pre-computed table for 16 different values, m to the 1, m to the 2, up to m to the 15. For the second iteration, we have to do squaring so that we can shift those 4 position to the left. So we basically square as 4 times, which is like making the power of 2 4 times. And then we had the multiplication with the second window. And we finally obtain the sign message. OK, this is when everything goes well. Now what if there is a faulty signature? What type of faults do we want to see? The message comes in. The first squaring iteration doesn't need to do anything. Then we do the multiplication to m to the power of the first window. And let's say that when we're doing the next set of squaring, a fault comes in. The only type of faults we like are faults where the faults come in during the squaring, it only changes 1 bit in my multiplication result, and they only affect 1 multiplication in the entire encryption. So if your microprocessor is doing a lot of mistakes, you're not going to get the good stuff. It has to do infrequent mistakes, but some mistakes, but infrequent, so that you can obtain signatures where only 1 bit can flip in only 1 multiplication during the entire signing process. And so we applied this and figured out how this could work in the fixed window exponentiation algorithm, but this idea to do a single bit flip was actually available in the theoretical project by Bonnet. So if I have that problem, at the end of my signature, what I obtain is a message that was squared. So the first window was just fine, then was squared a few times. At that point, what I model here, the single bit flip, is modeled by this component. A bit flip is either a 0 to 1 or a 1 to 0. So then that results in a plus or minus. And then 2 to the f. F is a position. I don't know in which position on my signature the bit has flipped. So that 2 to the f is saying one of the bits has flipped anywhere in the temporary number you had in computing your signature. Then I complete here my squaring operation, and then I add the second component. OK, so private key extraction. I give you the big picture of how we did it, and then we're going to go into more detail. So the idea is the client here has to send a number of messages to the server. See if this guy is coming back. The client sends a number of messages to the server. and it collects all the signatures that come back. The ones that are not faulty, we discard. All the other we collect, and I show them as red messages. Then we consider one of these signatures at a time. And the way we can extract those bits is not just nice, a few bits at a time. What we have to do is first the most significant bits, so the top window, then the second window, then the third window. So what we do is we try every message we got until one reveals a bit of the most significant window. The first message here did not. The second message, when we work with them, we get to extract the first most significant window. Okay, at that point, we take all our corrupted messages again, and we start again, and we look through all of them until we get somebody that reveals the next most significant window. And then we recycle all our messages, and we do this window by window until we get to the last piece of information. And how do we do the check? How do we know we extracted something? Because we have the message and the corrupted signature, and we have to guess some bits until we get the corrupted signature we collected from the server. So let's say, simple case here, let's say we guessed the most significant window. Maybe we guessed the most 5 significant window, but to keep it simple, let's say we guess the most significant window. That's my MDK. I know this number. I have the message, and I have DK, which are the bits of the most significant window. So my corrupted signature is modeled by this expression. The most significant window, the next window to the power of some, and then there is a bit flip in there, and then the rest of my signed message. What I have to do is, I know the most significant window. I need to guess the next significant window. It's a brute force guess, but it's for standard FWE, for standard fixed window exponentiation, is 6 bits. So you have to do 64 different numbers and figure out if one fits. You have to guess which bit got flipped. In a 1024-bit authentication, you need to try 1024 different positions and try brute force it. And then you have to figure out, there were 6 squarings operation, which of the squaring is the time where the faults arise. So you have to try all 6 positions. And if you do that, all 1024 error position, all possible error value, I forgot about that. You have to figure out if it's a plus or a minus. And all 6 squaring iterations, you may or may not find DK minus 1. If you do find it, you're golden. You move on to the next window. If you don't find it, you try the next message. OK. Now, there is an aspect I kind of left out because I'm always scared to flood people with too much math. But if you look at this expression, you say, OK, I know S hat. That's a corrupted signature that came. This I know because Valeria said so. It's the first part of my key. This I have to guess, I accept that. This I have to guess, I accept that. But I don't know all this stuff. I don't know DK minus 2. I don't know this 0. How am I going to figure out if this whole expression matches as S hat? So that's a problem I have to discuss. In our implementation, this whole thing, doing one check, so taking all the messages from one of these checks takes about 100 seconds. And in worst case, we need to check all 64 possible values for that window of the key. Sometimes, life is not so good. And you try all the messages you have, and you try all the combination, and nothing works. And what do you do at that point? You need to double up your window, try again. So now we take DK minus 1 and DK minus 2 and try them together, and we have to guess 12 bits at the same time. If that happens, it's painful. You may want to go and get some more signatures in the hope that it works, or you just try that. Now, I will say before, I cannot really work with this equation. I understand what I know, I understand what I don't know, but there is this whole orange stuff there that I don't know either, and so I can never figure out if the equation holds. Well, there is some math you can do to get out of that problem. And I'm going to go very quickly through that. But I basically multiply both sides by this expression with some unknowns. And I raise both sides to the e power. And if I do that, I get this differing expression, which looks more scary, but it doesn't have anything in it that I don't know. It only has number I knows and red things I have to guess. So now I can actually work with it. I just take a computer and make him do all those attempts. And I'm good. OK. So now let's look at our fault injection. So let's see if my system here is back on. So now what I would really like to do is to send some serious amount of messages to see if let's try even 129. The login didn't come through, 1 second. Okay, I'm going to do one last attempt of restarting this. I'm sorry for this. I think it got too warm. Okay. So I'll continue here. So the way we did this, we basically took the nominal voltage 1.5 and lowered that voltage, not too much, because we want to get some errors, but not too many faults, and collected a number of faulty signatures. Now, we did it with voltage, but that's not the only way you can do this. For instance, if your server is operating at a temperature that is higher than the recommended temperature, it may also start having the same type of problem where some signals are too slow. If you're overclocking the system, you may have this type of problem too. And then if you're going to Mars, that can create a situation where the alpha particles are too frequent and your SA server is doing mistakes. So some of these sources could actually be controlled. The natural particles is very hard to control, but lower voltage, if you have access to the system because it's a game console or your media player, that is, you have access to the voltage of that system. And a lot of data centers often are running at temperature that are too high. And so even if nobody is looking, they are doing mistakes every now and then. If you start monitoring that, you may, over time, collect enough information to do something with that. So we did a bunch of analysis of how do we get to the point where we get exactly the type of faults we want. So we start lowering the voltage. Look at the y-axis on the right. And the more we lower the operating voltage, the more the system starts doing mistakes. Obviously, at some point, it kind of avalanche. Everything starts being wrong. Then we analyze of these faulty signatures, how many of them are single-bit fault, the type of faulty signature we want. And what we found here is it's basically right on the verge of doing mistakes that we get the most density of the type of signatures we want. If you start having too many problems, then it's hard to collect the ones with single-bit problems. So we basically had to try to find the operating point where the server is just beginning to do mistakes. By analyzing, doing analysis of all the signatures we collected, we found that the faults were actually fairly equally distributed among all the 6 squaring iterations of the signature calculation. And then finally, we discovered this one thing, which after observing it, we could actually justify. The faults are not affecting, we had to try 1,024 different positions. We didn't find faults to be everywhere. There are actually positions that tend to be the one with the fault and lots of positions that do not. In practice, about 40 positions out of 1,024 are the ones that tend to have faults. So this chart here is showing how different bit positions have a different amount of occurrences of the fault. Now, why is that? It's again because we have a multiplier which is implemented in real logic. Some signal propagation are very short. They can always make it to the flip-flop, to the latch. And some tend to be on the critical path, and then they want most prompt to do problems. And so we actually exploited this. I was saying that every single check of every signal pair takes 100 seconds. We said, we're not going to check 1,000 bits. We check only 40 positions, the good ones. And so that way, we could take 2.5 seconds per check. That requires that you spend some time analyzing what you got first. But every type of multiplier, every type of microprocessor will show some repetition in this. There are positions that are more faulty than others. Okay, so what we did is we sent, I don't know, more than 10,000 messages to the server, collected back 8,800 corrupted signatures, and then we took all these signatures and we took all the windows you get in the 1024-bit RSA, and about 1,000 of these messages were useful. The others had problems in the prepared squaring tables, problems because there were multiple bit faults, problems because we could never use them to do anything of value. But we don't know which are the good ones and which are not until we get a few bits of the key out. So we have to try them all for every window we want to try. What we did is we used 80 different machines, because this is an easy parallelizable project, right? You can say 100 messages per machine. Everybody tries the same window with all the possible combinations. The first one to find the good results, send it back. We move on to the next window. It took us 104 hours using 80 servers. So this is the final results here of the physical attack we did. It was a 1024-bit private key using 6-bit window exponentiation. We sent 8,800 signatures that we collected over 10 hours. And then we have to do the offline analysis that took about 100 hours. OK. My last attempt to this. So here I'm trying now to send messages to my server and get messages back. Unfortunately, I think my voltage is a little bit too high. It's not doing a whole lot of mistakes. But this will take 2 or 3 minutes to run. I asked for 700 messages. My hope was to decrypt the entire key. We'll see how many we get and what we can decrypt. I can possibly, if there is time, do another run at the end with a slightly lower voltage to try to get more erroneous message. Now, the reason I don't really know at what voltage to do this is because it all depends on the operating condition. How hot is this room? How long has this been running? How hot is this whole environment? So, I'm tweaking the number to try to get in that little spike where I get a lot of single-bit error, but not too many multiple-bit errors. And it changes over time. But let me tell you a little bit about this setup first. So this demo is only running, is only trying to extract 128 bits RSA. Why 128 bits? That's super easy to break for pretty much anybody. Well, because I didn't want to keep you here for 100 hours. And so I thought, let's just get something done. So here, where is my pointer? So this series of question marks, every question mark represents 4 digits of my private key. On the left, I have a window that helps me collect messages. So I say send 700 messages to the server, and it will receive them back and immediately check how many of them are corrupted and how many of them are completely correct. After that's done, I'm going to try to run my analysis. The analysis will only go through the corrupted messages and try to extract which have been useful, meaning 1 single bit flip in one of the squaring operation, and so something useful to extract. How many messages were incorrect because they had multiple bits flipped, and so they were useless. How many were incorrect because the squaring table that we prepared before we tried to decrypt the message had already errors, because there were errors occurring when the server was trying to compute that table. And how many messages had multiple errors, and so they were useless because of that. Another thing that we try to optimize in the demo, not to keep you here forever, instead of saying, OK, let's take all the messages and try to figure out the first window. And then let's take all the messages and do the second windows. I just directly tell you, this message, let me figure out that window. And this other message, this other window. So you will see things kind of feeling at random. So now, as you can see, these guys start going through the messages. So well, it's going to be done pretty quick. 31 messages, 16 were useful. And those 16 allow me to discover these digits on my key. Now, on this plot here, I'm showing the fraction of useful message, the fraction in red of multiple bits flip, and the function in black there were multiple squaring table errors. On the middle chart, you can see which of the positions, 2 to the f, which of values of f actually were responsible for a bit flip. And it's obviously a different chart than what I had in my 2024 extraction, but you can already see from here that there is a pattern. Some positions are more prone to be the one carrying the fault than other. And the last plot just shows over time how many windows were discovered. Ideally, I would like it to go up to 232. So I'm going to move on to the next part of this talk, but before I do that, I lower the voltage by 1 decimal point, and I'm going to kick off another run, and maybe it's going to give me a little bit more information. OK. So the next part of the project is we said, lots of people complained and said, who gets to touch the voltage of a server? Servers are usually in a vault inside a bank in a data center. And you said, well, really, that's true, but there are also all the consumer devices that do RSA authentication that are in the customer hands, and you can extract your private key without even your provider knowing about it, because you don't damage anything. But then we said, well, let's look at the temperature attack, because those servers in the banks and in the vaults tend to run hot, and maybe there is something we can do there. So this actually was a class project that some graduate students did. They took the same board. Indeed, guys, to come to this presentation, I had to buy a new board and a new memory because they burned that thing so bad that it was completely unstable. Okay, so this is like new equipment. But they took a heat lamp and put it right really close to the processors. And they also, it's kind of in the dark there, there is a little, how do you call it, area heater. Okay, so they tried to create some good heat. And then they had a sensor, temperature sensor here, and the probe was put right under the chip, between the chip and the board. And that's just a reference. I mean, the temperature of the chip is really not the same as the one between the chip and the board, but it's something so we can work with some numbers. They started, being a class project, they started with 128-bit RSA, and they were actually able to extract the private key. They had some problems at the beginning because there were temperature runaways, meaning the processor would get hot and start doing mistake, and that temperature will make it even hotter, and then everything will be broken, and there is nothing useful for me. So then they figured out, I need to put a heat sink so that I don't have this positive feedback, and in the couple of minutes, all my signatures are broken just because the thing is heating up. But they basically figured out that just with temperature, they could extract the entire 128-bit RSA. They were using 1,000 signatures, and they were helping it a little bit with the voltage. So they didn't have to lower the voltage so much, but they were keeping it already on the verge because they couldn't really put it in an oven. Then they said, OK, let's move on to 1,024-bit RSA. And they got something. They obtained 283 corrupted messages out of 1,000. 91 of them were useful. And as a result, they got 30% of the private key out. The challenge there was that the response of the system, so the faulty messages versus temperature, was a very steep curve. And so, they were working, sending messages, and there was a guy there that would hold the heat lamp at the right distance to try to get the right temperature. Now, these people had a deadline. They have a month and a half to do the project, after which they failed the class. But if you have time in your life, you can just connect to a data center and wait. And broken messages will come to you, and hopefully over time, you will have enough to do your work. If nobody's grading you, that's doable. OK, so here I'm trying to conclude. So transient faults are something to worry about. And this is actually the reason we came to all this research. My main field of research is reliability, no security. And actually, this was meant to be a fault analysis platform. We created all this setup so that we can create a circuitry that is equivalent to injecting the fault and see the impact on the operating system or on the application the users are running on the operating system. And there is another research group at University of Urbana-Champaign that is also working on reliability, and there's a software approach to it. And so they basically detect when there is a system crash, a high-level system crash. They cannot detect silent data corruption. Those faults modify the results, but you don't notice anything. It's just the wrong result. And so we were just, their claim is basically silent data corruption. They don't really happen. They're not really important. And we were trying to prove them wrong on that. Silent data corruption can actually have a big importance. And that's how we came to do this. So I guess one of the messages I want to deliver is faults are something to be concerned about. So faults are something that it's important to be protected from. And given how silicon technology is scaling farther and farther, the impact of transient fault is actually growing because smaller transistors need much less energy to switch because of an energy particle. What we attacked was OpenSSL 0.98 in the fixed window exponentiation algorithm. That hasn't changed even in the current version. However, OpenSSL says that if you run it correctly with their standard settings and flags, blinding is active in the server. Now, blinding is a feature that was originally designed to prevent timing attacks, but it will prevent this attack too. And what it basically does, it modifies the message before it encrypts it, and then modifies it again after decryption. It completely breaks my system because now my M is not the M I know. And so I'm missing one component in my own monster equation. I have to tell you that from our end, when we even started this project, we didn't know about blinding, and we didn't know about flag. We didn't touch OpenSSL, and somehow we bypassed it completely. It's very possible that consumer electronics, trying to save time and computing time on devices that try to be low power and small, bypass blinding. It's very important not to do that, though, because it exposes you to this type of attacks. Little take-home message for, I would say, all of you, because all of you are very security conscious. Obviously, keep all your software updated. That's something you obviously do. But there are other things that software people don't often think about. Do not overclock. Overclock can lead to your processor doing mistakes you will never notice. And that, if you're unlucky, can be a problem for your security system. Keep the system cooled properly and avoid power fluctuations. That's another thing that are typical of data centers. And from my reliability standpoint, even if a system that doesn't operate in normal operating condition doesn't crash, and so it looks like it's working fine, it can cause silent data corruption, which are the nastier type of fault, because you don't even know you have a fault. And so you will never do something to protect yourself against it. Okay, this concludes my talk, and thank you very much. Does anybody have any question or no questions here?
Hello?
Yeah, I can hear you.
Oh, good. The question I have, if I recall correctly, and I just tried to look it up again on my phone, and it seems to be the case, the Leon core is actually designed so that many of its data paths are resistant to single-bit errors. And I wonder if, in a way, that may have made you lucky enough that the errors you were injecting were far less likely to affect the control
Can
flow.
you be closer to the microphone? I heard that the Leon core is designed. Yes, just stay close.
Okay, this is better. I was saying that I believe the Leon processor core is actually designed so that many of its data paths are resistant to single-bit errors. And I wonder if, in a way, that made you somewhat lucky because perhaps the errors you were injecting were less likely to have fatal effects on the program's control flow. And is that the case? And if so, is this attack harder to practice against commodity processors?
So I think what you are referring to as a protection against single-bit flip errors is error-correcting codes on the register, like ECC on the register. So if I write a value on the register and then something happened and value changed, I will notice. Okay? That's a very classic type of protection, particularly for caches and small memories. In this case, the register will never see the problem. The value comes to the register broken. It will be stored broken, and the ECC code is generated for that broken value. So it completely bypasses this type of protection. Well, the protection you're talking about is very valuable because it protects against transistors that fail and start storing their own values, which can happen when the chip ages.
Well, I guess what I'm actually trying to ask is, a resilient chip design like this, are you in fact getting lucky in that the errors you're injecting are not, for instance, causing a branch to a wrong address or an invalid and access to an invalid memory location or something that would simply take the core offline rather than producing the single bit error in the multiplier that you want.
So you say, am I getting lucky because I'm doing something that does little mistake instead of destroying the whole system? Is that what you're asking me?
I'm asking if, is this attack easier to run against a hardened processor core like this than against a commodity processor?
So I don't believe that's the case. If I lower my voltage by another 0.1, it would be a complete failure. However, in this processor, and that's true for pretty much every microprocessor out there, the multiplier is a very complex component in terms of combinational logic, and it tends to have the longest data path. So if you have a system that starts doing something wrong, chances are it's going to be in the multiplier. If not, it will be the divider. But if you're not using the divider can do whatever it wants.
Thanks, that makes sense.
Hi. Was your server using the Chinese remainder theorem?
I cannot hear. Is a server?
Was your server using CRT, the Chinese remainder theorem?
We directly asked the server to do the fixed window exponentiation. We skipped that phase. The standard OpenSSL calls first Chinese remainder theorem, checks that. If that fails, call fixed window exponentiation, does not check that for a matter of time.
Okay.
So we call directly the FWE function of OpenSSL. That was not touched.
So if the Chinese remainder theorem, like if that method starts showing errors, why wouldn't you just have your server stop? Like it seems like that shouldn't happen under normal operating conditions, right?
Yeah, that's more of a question for the OpenSSL people. So I think the Chinese remainder theorem algorithm is very prone to errors for any little attack, conscious or unconscious. And so, and it's very fast. And so that's the first one you want to use if everything goes well, because it's easier to check than to encode and decode. And so if that fails, then they go into fixed window exponentiation. Why didn't they check the fixed window exponentiation too? Matter of time. But if you ask them, they would just say, well, you're also supposed to be using blinding. So at that point, if something goes wrong, it's an act of God. Because if somebody was attacking, I'm still safe. I don't know. They choose the sequence of algorithm that they call. And it's a very well-thought process to try to get good results in a decent amount of time.
Hello, can you hear me?
Yes, I can. But if you stay closer to the microphone, I can hear you better.
Were the bit position errors the same for temperature variations as well as voltage variations, or are they different?
I say they should, but I don't have actually a check on that, because there were two different groups of people that did the tests. Because of the cause of the failure, they should, but I cannot prove it to you. Okay, thank you very much.